on your background, whether you're coming from software engineering background or from database background. If you are coming from software engineering background, you can leverage those skills that you already maybe have experience with to do data modeling. Okay, although in object-oriented modeling we go beyond just data modeling, because in an object, this one at the end of the day will produce a class diagram, and this one will produce, yes, an ER diagram. They are not exactly the same for sure, but there's a lot of overlap. They're somewhat similar. Of course, in a class diagram, we don't just have the attributes and the data about the classes. We also have the behavior, the methods that are offered by every class. But there's a lot of concepts that overlap. For example, I just mentioned multiplicity. We call it multiplicity in object-oriented modeling. We call it cardinality in a relational database. But it is exactly the same concept. Now, this weak entity, I think it's easier if you are coming from an object-oriented modeling to understand weak entities rather than trying to understand it from a database perspective. Let me just super quickly explain this. In object-oriented modeling, instead of talking about entities, we talk about classes. Okay? So this is just an example. So for example, I have here a customer, and I have here an account. Okay, and of course there is a relationship between these two. In object-oriented modeling, this relationship, we call it association. Relationship between two classes, okay? And in here we do multiplicity. For example, a customer can have one or many accounts, and an account belongs, let's say, to one customer for simplicity, okay? Now, in here, in object-oriented modeling, we ask ourselves, is the account part of the customer? Do we have a situation where we have a whole and a part? We don't have this scenario. Let me give you another example here. If I take, for example, a car, okay, and I take an engine. These are two classes. Of course, there is an association between them. And a car has one engine, and an engine belongs to one car. Now, this is an association, but it is special type of association because this one represents a whole, and this one represents a part. Okay, and then basically what we can upgrade this association. We will call it aggregation. This is what an aggregation is. In UML, we represent it as with a diamond, and the diamond we add it to the whole side. Okay, so this signifies an aggregation. Okay, it is special type of association where we have whole and part relationship. There's a whole and there's a part relationship, but each of them has a separate lifetime. What I mean is, we can have a car, and the car could be destroyed, but the engine can keep living. I mean, the engine can exist without the car. In fact, a car could be written off, you cannot drive it anymore, but the engine, you can take it, they can take it to Sinaiya and sell it as an engine, and you can place it in another car, or even as spare part, whatever it might be. But the engine lifetime is not dependent on the car. Okay. Now, let's take another example, which is basically, let's say here, a building and a room. First, there is an association between the two. So a building has many rooms, and a room belongs to one building. Now, is there a whole and a part relationship? Yes, the whole is the building, and the part is the room. Okay, so we can upgrade this association to an aggregation. So to upgrade it to an aggregation, what I do, I put here the diamond with the whole part, and I draw my line. Yeah, and then I ask myself, can the part exist in a meaningful way without the whole? It cannot. because if the whole is destroyed, the part is also destroyed. Yes? So I can upgrade this. This is called aggregation. I can upgrade this aggregation to composition. And then how do I make a notation? How do I express this in UML language? By filling this diamond. So the filled diamond, if we see a filled diamond, it tells us a lot of information. It tells us this is a whole, that is a part, and they have the life of this part is controlled by the whole. The whole does not have a life cycle on its own, or a life on its own. It cannot exist in a meaningful on its own. Okay, so in ER diagram or in data modeling, this is called a weak entity, the one that cannot exist on its own, or does not have a meaningful way, cannot exist in a meaningful way by its own. It's called a weak entity. That's what's basically a weak entity. A weak entity is kind of owned by another entity, and we should have the owner before we can have that weak entity. That's what weak entity means, okay? And the implication of this in terms of data modeling, if I continue on this, let me just bring this. So you can see here in object-oriented modeling is the abstractions and the way you can think of it is much more powerful. I find it anyway, maybe I'm biased, and more meaningful. But anyway, this is a weak entity. A weak entity is an entity cannot be identified by its own attributes alone. So for example, here is a weak entity. Let me see, can I use this? No. Okay, here is a weak entity, which is a room. It cannot exist on its own. It's really heavily dependent on the house. So the way this is a candidate key of the room. So a room maybe have a unique name. For example, there is Ibn Khaldun, there is a library, or some part. This is CS emitter room. Let's say the unique identifier is the room name. So this one cannot be the primary key of this entity. Because it is a weak entity, its primary key must be made by its partial key plus the primary key of the owner entity. That's what weak entity means in terms of data modeling. So what will be the primary key at the end of the day? What will be the primary key of the room? It has to be the house number plus, in this case, the name. Or it could be the room ID or something.
Like the number of that, or the ID of the room and the college, for example.
The ID, yeah.
Events in the building.
Yeah, that is just a way of codifying. Like, for example, yes, it's a good point. Like, even for codifying the rooms. For example, my office number is C07-132. So C07 is the building ID, and 1232 is the actual ID of the room. So because the room is a weak entity, its identifier is made up of two parts. The primary key of the owner entity, and then the partial key of the weak entity. That's all. That's the story of this weak entity. So you need to be aware of it, because it cannot exist independently. It cannot have its own primary key. Its primary key is composition of the primary key of the owner entity plus what we call the partial key of the weak entity itself. That's all. That's all there is to it.
Do you call it primary key or foreign key?
No. In here it is. Yeah, it acts. Yeah, this is a good point. This part here, it acts as a foreign key to the house. Yes, you're right, as a foreign key to the house. But a composition of these two fields make the primary key of the room. Okay, so that's all there is to it. So when you hear this weak entity, that's what it means. It's an entity that cannot exist on its own. Its existence is related to the owner entity. Okay, so, and the implication of this is that the primary key of weak entity is made up of the primary key of the owner entity plus the partial key belonging to the weak entity. Yes, please.
In real life, did we have to use composite key or use another different key sequence?
Okay, now, so in practice, many developers tend to no, first of all, we need to recognize that this is the primary key. Now, in terms of implementation, in terms of actual implementation in the database, many developers tend to create like kind of what we call surrogate key, I think. It's kind of, it's a key that is typically auto-incremented number. And the reason why, for example, I might have here a room ID, and it is an auto-incremented sequence, 1, 2, 3, 4, and so on. And the reason why people do this is that when they want to link this room to another entity, let's say there is an event will take place at a particular room, so the event will have a foreign key pointing to the room. So instead of having I copy these two columns, which to represent the foreign key. So the foreign key, let me make it, especially those of you not familiar with this. So in here, let me just quickly do this. So this is our building. Okay, this is like, for example, ID or code, building code as a string, just as an example. And this is a room. So one to many, 1 to n, okay. And then, okay. So in here I will have the building code and, sorry, the room code, yeah. Let's say both of them are string. I think it is important to recognize that both of these guys are the primary key of this entity. Yeah. Of course, this one is also acting as the foreign key linking this entity with the building. Yeah. Now, suppose we have another entity here, which is event. And let's say it has an ID and it has a title. ID, let's say, of type int, and it has a title of type string, let's say. And it will have a room or a location where this event will take place. Now, so definitely we will have to define some kind of foreign key. We'll have to define some kind of foreign key that will link the event with the room. Okay, so if we use this composite key, we have to take the way we establish a relationship, because remember there will be a relationship like this. So room can host many events over time, and an event is taking place in one room. There's a one-to-many relationship. So the way we establish the one-to-many relationship, we take the primary key of the one side and we put it as a foreign key in the many side. That's how we establish a one-to-many relationship. So if we want to do it, what we will be doing here building code and the room code. Okay, that's one way of doing it.
Like copying again?
No, not copying. No, basically, in the structure, in the definition or the schema of the event entity, we'll have these two columns. Yeah, to be able to link the event with the room. That's the only way in a relational database. a one-to-many relation, to establish a one-to-many relationship. In fact, this is mechanical, even if you don't understand it. That's how we do it. We close our eyes. If there is a one-to-many relationship, we take the primary key of the one side and we put it as a foreign key in the many side. Yeah. Now the issue here, the primary key of the one side is a composite key, which means it has multiple attributes acting as the key. So I need to basically take these two attributes and add them to the schema of the event. So this is fine. This could be nicely done. But some developers, they find it like a bit tedious or a bit cumbersome to have this composite key. So to overcome this, they will create some other key, which is not natural key. It is like a fictitious key. Just an ID, and it's int usually, and it's auto-incremented. Depending on which database you are using, for example, in SQL Server, you just go to a particular column and say this is an identity column, and the database will auto-increment it. I think in Oracle they have sequence. It goes and auto-increment that. And then instead of copying this composite key, they don't do this. They will put here room ID as the foreign key. Yeah, it's just not to replicate this. Either way is fine. But this is very common to make the establishing the relationship much easier. Especially when you have a composite key that has more than 2, 3. Sometimes there are 2, 3 columns, 2, 3 columns that make up the primary key. Yeah. So this is just, there is no kind of a right or wrong, but this is common practice. I have seen it very, very often with developers. But we really need, in terms of conceptual design, we really need to be aware or establish that the primary key, the natural primary key of the room is a composite key made up of the built-in code coming from the owner entity and the room code coming from the room entity, and this is the primary key. And the reason why it is composite, it is because it is a weak entity. That's what a weak entity is. It doesn't have an identifier on its own. It relies on the primary key of the owner to establish this uniqueness. Because every entity, by the way, every entity must have a primary key. We do this part of the conceptual design. Yeah, it's just a weak entity. Usually, most of the entities, except if they are bridge entities that we will see shortly, the key will be composite. But most entities, the key will be one key, typically, in most cases. Okay. But for weak entity, by definition, the key is composite key. One part coming from the owner entity, and one part coming from the weak entity itself. Clear? Now, when there is a relationship, you have the choice. If you want to follow really the relational model, you just kind of the composite key, put it again in the many side. If you want to make it more convenient, you can create a surrogate key that is like fictitious key. It's not natural key, auto-incremented, and you add that one to the many side to establish the link. Yes.
Why we can't use the room code to be the foreign key for the event instead of doing another ID?
The room code.
Is it like the primary code?
Because we might have the same code in different buildings. So we might have, like, let's say, in my office, for example, I have Office 132. They could be Office 132 in the business building, which is maybe C08. Or it could be in the medical building. So you might have, which is true. I mean, there are office numbers and classrooms, same number, but they belong to different buildings. So the room number itself is not enough to uniquely identify the room. We have to make it composite, where with the built-in code plus the room code makes it unique.
So here will be the built-in code plus the room code will be both primary key for the...
Yes, the composition of the two. In fact, just to show you this concretely.
And why would you choose the ID to be the primary key of the room?
Sorry,
the ID, the new one.
The new one. This is kind of some developers do that, but if the real relational model it's not supposed to do that. You're supposed to use natural keys as much as possible. People use that just for convenience because they don't want to add these two column composite keys to the many side table. Just to show you this concretely, when I create a particular, I'm not sure if this will work. Sorry, let me just. Okay. Just to show you quickly, so if I go here, it doesn't matter anywhere, just go here and create, let's say, table here. This is the room code, which is, like, let's say int, keep it simple, int, and the built-in code, which is, keep it simple also, char 3. Yeah. So basically what I can do, I select these two, and these will become my primary key. So my primary key in this table is made up of two keys, two attributes make up the primary key. Yeah. That's basically the idea. I can make the primary key a composite key. Yeah. All right, moving on. Any questions? Yes.
But this is not mean that any composite key is weak. An entity that has...
No.
The relation is not...
Not necessarily. There are other cases where we need to have the key is a composite key. Okay. There are other scenarios. Okay. In most cases, let's just take an example from my little system. It's not ideal system, but just to give you an example. Faculty, there is one key only, faculty ID. Document. Usually there is one key. Most of them have one key. Criteria ID. There's only one key. In most of them, but we will see. Shortly we'll see some scenarios where we have composite key. Okay. Now, next thing I want to show you is in ER diagram, there is a normal ER diagram where we have basically entities, and entities can have relationships, and a relationship can have cardinality that we just discussed. There is something called extended model, ER diagram, or extended entity relationship model, or extended entity relationship diagram. And what this extended entity relationship diagram, it supports the concept of inheritance and subclasses. Okay. Those of you familiar with object-oriented modeling, this is a very common abstraction we do in object-oriented modeling, where we have superclasses and subclasses. So what is the idea of this inheritance? Well, basically we establish an inheritance relationship between classes. You can also do this in entity relationship diagram. You can have super entity and sub entity. So what's the idea here? First of all, why are we doing this? Yes, very good. So basically we are trying to reuse, we create a schema. We take the things that are common between those similar entities. We take the things that are common. We create one entity that is super entity. And then we have sub entities that will inherit those attributes and maybe add some extra attributes. Okay. This is very well established in object-oriented programming. So in object-oriented modeling, and of course in object-oriented programming. This doesn't mean the database supports this. Database does not support this concept of inheritance. But in the modeling, we can take advantage of it. It would be nice to recognize that these entities are similar. They have lots of things in common, and they have some specific things. This is in the modeling part. In the implementation, it's a different story. There are various ways of mapping that hierarchy into actual tables that will be created in the database. But let me first show you a small example of what this really means in terms of object-oriented modeling. The typical example is let me put it here. The typical example is let's say, bank account. So we have account. So for example, for account, we might have, or let me give you a much simpler one. For example, QU member. So all of us here, we can be, in general, if we do generalization and high-level abstraction, we can consider ourselves as QU members. We have a lot of things in common in terms of attributes. We all have an ID. We all have first name, last name, date of birth, nationality, and so on. Yeah, lots of things in common. And then within the QU members, we have subclasses. Yeah, we have student, and we have faculty, and maybe we have staff or admin, let's say staff. Yeah. So they all, instead of defining attributes, repeating ourselves in each of those entities, we take the common attribute, put them in the super entity, and then we say out to ourselves, what is unique about student? What are the attributes that are unique to the student? So maybe GPA, or maybe the measure. And that's it. Maybe, at least for now, these are, yeah. Now for faculty, what is so unique? Faculty, we can capture it in ID. We can abstract this, but all of them have ID. You have student ID, I have staff number, which is kind of both of them. Yeah, maybe here office number. Office number of type int or string, let's say. Okay, staff, what could be so unique? Sorry? Courses they are offering is something different. So we can model it, we have to model, there's a big story to model it. So we cannot capture it in the faculty entity. Yeah, we have to capture it somewhere else and link it, establish a relationship. But as faculty, that's all we can put. That's for faculty themselves. What's something that is extra compared to other QU members? Maybe is the office number, maybe salary, maybe. Although the staff also have salary. So staff, maybe position, I'm not sure. For faculty, it could be like no, not the college.
Degree?
Not degree, maybe the rank, assistant or associate, or maybe the rank. Let's say call it here rank. We don't call it position, we call it rank. But maybe here we call it position. It could be secretary or manager or director or so you get the idea. The idea here, and in object-oriented modeling, we express this in UML notation. We put this rectangle here and basically this is a superclass, and these are subclasses inheriting from the superclass. Okay, so in object-oriented modeling, this is very common. Anybody coming from that background, they are very, very, very familiar with this. Now, in database, try to do the same, but they call it basically subclasses and extended entity relationship diagram to make the entity relationship model aware of this inheritance technique. It's just to have reusability. Okay. Now, in terms of how it is represented in ER diagram, you know, I'm not really, maybe I'm a little bit biased, but you can see the UML much cleaner to represent things. This is how it is represented in ER diagram. So they put this circle between the two and then link the sub-entities this way. And also within the circle, you can see here, they put either D or O. This is very important. So what's the difference between these two? Between when you put a circle with a D and we put a circle with O. What does that mean?
You just want to be innovative here.
No, not really. No. It has a significance, and it has implications in the actual implementation, of course. Major significance. So in here, when you put a D, basically this is called disjoint constraints. Disjoint means that the employee can only be one of these, cannot be multiple of those subclasses. So if you have an employee, they are either a manager or engineer or technician or secretary. They cannot be manager and secretary. They cannot be manager and technician. One of these, mutually exclusive. So this inheritance relationship, it has a disjoint constraint. What disjoint constraint means, the superclass can only be one of these subclasses. We cannot accumulate multiple. But in the other one, it's overlapping. Overlapping means, let's say a person can be any of those, can be employee and can be customer. Okay? I'm sure you have seen like people work in Carrefour and they buy stuff and they also queue with us and check out. Yeah? So they are putting two hats. One hat as an employee, another hat as customer. Okay, so in this case, it's an overlap inheritance. And the other one is disjoint inheritance. Yes? Okay. And you will see the difference when it comes to the actual implementation. Translating this actual conceptual model to the logical model that will be implemented in the database. Yeah? Okay. That's basically the main idea of extended ER diagram, where we have the concept of subclasses. And as I explained, the idea is we take the common attributes, we put them in a super entity, and then we have sub-entities that inherit those common attributes, and they can extend the superclass by super entity by adding extra attributes specific to them.
Also, the behavior can be inherited.
Yes, but in here, like basically, I try to explain it here for the people coming from OO background. In object-oriented in object-oriented modeling, we don't limit ourselves to just identify the attributes. In data modeling, we only identify attributes. We don't come near the behavior. Okay, but in object-oriented modeling, not only we identify the classes which are equivalent to entities, we also not only identify their attributes, identify their behavior, which means I assign some functional responsibilities that those classes will do and will implement in terms of methods. But of course, inheritance in object-oriented modeling and object-oriented programming, you inherit both the attributes and the methods. But I mean, this is in terms of object-oriented modeling. In terms of subclasses or sub-entities in entity relationship or in data modeling, of course, we only talk about entities only have attributes. They don't have any behavior associated with them. Yeah. But the concept is the same. The concept is the same. And by the way, the relationship between them is a. So this is important because sometimes we get confused with inheritance. Inheritance, for you to make sure you got the inheritance right in terms of modeling, always read it from subclass to superclass and make sure it verifies this check-in or this verification point to say student is a QU member. So this is valid. Faculty is a QU member and staff is a QU member. So this way your inheritance modeling is correct. Because if they don't meet this constraint here, then you are not talking about inheritance. Maybe you are talking about something like this. Maybe you are talking it's only association or aggregation or composition.
There is also has a.
Which is this is the aggregation, has a aggregation. Okay. The composition is also has a, but the part cannot exist on its own. Yeah. So in object-oriented modeling, definitely is more mature and much more clearer. The abstraction it's much more powerful. In object-oriented modeling, basically the association between classes can only have 4 types of associations. What are these type of associations between classes? It can be association first. Yes, association is the kind of the entry-level relationship. It can be upgraded to aggregation if it's a whole and part, and aggregation can be upgraded to composition if the parts cannot meaningfully exist on its own. That's one type of relationships, and there is a special type of relationship which is the inheritance relationship. That's one you need to be careful. With inheritance, you need to check that the subclasses satisfy the is a relationship with the superclass. Otherwise, your inheritance has problem. Yeah, exactly the same way if you apply this to your entity relationship diagram. Exactly the same concept. Okay. Okay, so that is the idea. And by the way, if I go this way, if I read this way, I'm doing generalization. I generalize the things that are common, put them in the common superclass or super entity. If I go this way, I'm talking about specialization. I'm inheriting the common things and adding what is specific to each subclass. It's just terminology, generalization up and specialization down. Okay. This one I already explained in terms of disjoint. For example, an account can be either saving account or current account. It cannot be both at the same time. This is called the disjoint constraint. Overlapping constraints, the super tab could appear in many of the subtypes. So, for example, a person could be a customer and employee. In this case, we are talking about an overlapping constraint scenario. And this is how it is written in terms of modeling when you do it in ER diagram. Okay? Of course, the tools, as we saw last time, if you remember in visual paradigm, one of quite widely used tool, they are more influenced by the class diagram rather than the ER diagram. So if you use the pure ER diagram, in professional tools, you might not see this. You might not see this type of notations. In professional tools, how do we represent an entity? Similar to a class, with a rectangle with 2 parts, the name of the entity on top and then the attributes. This one is more kind of academic, just to kind of get started with the modeling. But when you go to practice, it's more like a rectangle with the attributes directly beneath it. Okay. All right. So let's say we did an ER diagram. Of course, this discussion will make more sense if you use kind of traditional academic ER diagram. If you use professional tool, the professional tool will provide for you a logical model ready to deploy to your database. And I kind of tried to show you last time on the visual paradigm. We picked up one of the examples that come with the visual paradigm, and we were able to generate an SQL statements to create the actual database in the database engine that we selected. Yeah, but still, there are some concepts that are still relevant, and you need to be aware of them, even if you are using these professional tools. So I will just go through them quickly. There's a little bit of terminology problem in the database world. Not problem, but a lot of terms that they mean the same thing. Entity, relation, table, they all mean the same thing. In the conceptual model, we call it entity. In the logical model, we call it relation. And then when we create it in the actual database, we call it table. Okay. Now, in the logical model, or in conceptual or logical, we'll talk about tuples or tuple, which is the row. In the physics, when we create a table, we don't talk about tuple, or even in professional world, they don't talk about tuple. They will talk about rows. So tables and rows. Okay, just be aware of these terminologies. These are common sense things. Every relationship has to have a unique name, of course. Every attribute value should be atomic. Like every column or every attribute, you should not store, you should not allow in your data model, you should not allow storing multiple values, either comma delimited values or an array or a list. Forget about that. If you have that scenario, you need to do something about it. And that's what I will explain later in what is known as normalization. Okay? Every row must be unique, which means the entity must have a primary key. Okay? And you try your best to find out go through your attributes and try to select one of them that uniquely identifies each record in the table. This is important. This is important because that primary key will be used for linking entities with each other or tables with each other. So you need to have each record must have a unique identifier known as the primary key. Okay? If you run out of all options, then you create a fictitious one, an ID that is auto-generated. But you don't go for that unless if you don't have any other choice. Okay. The attribute in a table, of course, the attributes have unique names. These are common sense. The order of columns and the order of row is irrelevant. So whether you put ID first name, last name, or ID last name, first name, it does not matter in terms of relational model. Yeah? There's no difference between these whatsoever. Okay. So the primary key, as I mentioned, is one of the attributes or multiple attributes that uniquely identify each record or each tuple in our relation. Yeah? It could be a simple one, which is a single field. Again, field, attributes, column, they are all used interchangeably. Or it could be composite, more than one field. Or it could be surrogate key. This is how we spell it, surrogate key, which is basically an auto-incremented ID, auto-generated. Yeah, as I showed you before, maybe in a SQL database, it is an auto-generated. The way you do that, for example, or let me just put it here. For example, here, room ID int, and then basically I can here something called identity specification, and I say this is an identity. Why it's not allowing me? Because maybe I already have a primary key here. Just remove this. Yeah. Yes. You see here, this is an auto-incremented number, and that's how I do it. In other databases, they are known as different things. Maybe in Oracle, as I said, sequence. In other databases, different technique. to configure this. But at the end of the day, these are called surrogate keys. And keys are usually used for indexes to speed up response to user queries. We will see this. We'll spend a lot of time discussing this later on. Okay. There's one more thing when it comes to logical model. In the conceptual model, we don't talk about these concepts. But in a logical model, because in a logical model, that's it. Next step is to generate our database or to go ahead and write the SQL statements to create our database. So all the details now we have to capture them, including the primary key, including what is known as referential integrity. What this referential integrity means, if I have a one-to-many relationship, for example, between entities, let's say I have an order and an order item. So in the order, I put the order details, the order ID, the date of the order, the customer ID. Now the order has many items. It could be, let's say, milk, vegetables, whatever the items might be. So referential integrity means I cannot create an order item for an order that does not exist. Which also means before I create the order item, what should I do? Create the order first. I create the order, get the ID, which is the primary key of the order, and then use that ID in the order items. So every order item I create, one of the attributes of the order item will be the order ID. So I can link the two in a one-to-many relationship. So referential integrity is something built in the database. If you try to create if you try to create a record for something that does not, if you try to create an order item for an order that does not exist, the database will throw an exception and it will not allow you to do this. This is a referential integrity. Same thing. If you have, let's say, customer and orders. You see here there is a one-to-many again. A customer has one or many orders. So before you create an order, you must create a customer first. And then you take the customer ID and you put it with each order you will create later on. Now, if you go to the customer class, the customer table, and you try to delete a customer, and that customer has orders, the database will not allow you to do this, okay? Because it will break the referential integrity. You will end up with what is known as orphan records or orphan rows that don't have their associated parent. Yeah, you will have order items without an order, or you have orders without a customer, or you will have courses taken with grades without a student. You don't want to end up in that situation, except if you ask the database to do so. So there is something called the cascade update and cascade delete. So for example, if I have a customer and orders, okay, and then I can configure the database to say, oh, by the way, if I delete the customer, go ahead and delete all the associated orders. This is very, very rare. People don't do this, but database has this feature. You can do this. Hopefully I can show you this quickly here. Maybe I have a diagram here. Yep, hopefully I have a diagram. Okay, so for example, here is faculty with project or with project evaluation. So faculty has one or many project evaluations, yes? And here in the project evaluation, basically the faculty is basically the examiner ID. The examiner ID is referring to the faculty. So if I click on this one, this is a relationship. Click or say properties. Yep. See here properties. Insert and update specification. Here delete rule, no action, and update rule, no action. Means if I try to delete faculty from here, and if they happen to have an evaluation, the system should not allow me. Yeah. But if I wish, I can override this default behavior. I can say cascade which means if I delete, the faculty delete all the evaluations they have done. Yeah. Let me try it. Hopefully I won't break anything. Okay, so if I do here select star from faculty. Okay, let me just see. At least I can fix mine if I make a problem. Okay, here's my ID here, where ID 1, 2, no, 7, yes?
Faculty ID.
Okay. Just to make sure, here it is. And then I'll go ahead here and delete. According to the referential integrity, this should fail. Yeah? Okay, yes. So it says here delete statement conflicting with this project faculty. There's one constraint here called project faculty project. So basically faculty has one or many projects. So definitely I cannot delete. Okay. Unless if I go to that relationship and say, oh, by the way, cascade the delete. If I delete the faculty, delete the projects. Yeah. Even if I remove this, it will still not work because the faculty have evaluations. I have to go and delete, and either delete the evaluations or ask the database to cascade the delete to the many side. You see, this is what I mean by referential integrity. By just establishing, by the way, just by establishing these relationships between entities, automatically the database will enforce this referential integrity constraints. Yeah? Okay, good. Same thing for inserts. If I try to insert, let's say here is a project. Where is the project? Here is a project. One of the attributes of project, period ID, for example. You can see something called period ID. Is period ID. If I try to insert a project for a period that does not exist, this should fail, for example. Yeah, and so on. Okay, that's what referential integrity means. And in modern databases, you just establish the relationships, and these are automatically enforced. Okay. This is just to give you some examples of keys and how these keys are very, very important to establish relationships, and why every entity must have a primary key. So this is a very common example. So this is a customer table or a customer relation. Let's talk about tables now. Yes, yes, please. Oh, okay. Oh, already passed. All right, so let us break maybe for 10 minutes, and then we'll come back. Okay, so I try to be a bit quick now to try to finish this. So in here, I just want to highlight the importance of keys and the importance of every entity must have a primary key, because using the primary key, we use the primary key to establish relationships between entities. For example, we have here a customer entity, and the primary key is definitely the customer ID, which is a unique identifier. So if we want to establish a relationship, a one-to-many relationship between customer and order, this is in our conceptual model. In our conceptual model, we have established that there is customer can have many orders, and the order belongs to one customer. So this is the one-side table, and this is the many-side table. So the one-side table has a primary key, and the way we establish this one-to-many relationship, we take the primary key of the one side and we place it into the many-side entity. And that's how we establish the one-to-many relationship. This is very important. So the order table will have its own primary key, of course, which is the order ID is the primary key of this table. But the way we will link it with the customer is through this foreign key. And the foreign key is nothing but the primary key of the one side. Yes? Now for this one, which is we have an order and we have a product. So if I try to quickly put this one here, here is the order, there is order, and there is a product. In our conceptual design, we established that there is a relationship between these two entities. An order can have multiple products, and a product can appear or can be ordered or can be part of multiple orders. So this is a many-to-many relationship between order and product. So this is in the conceptual model, it's fine to put like this. But when it comes to logical model, which is the step before we create our database, in a relational database, this is not supported. You cannot have a many-to-many relationship in a relational database. So we have to translate this into one-to-many relationships. The database, the maximum it supports is one-to-many relationship. I mean, a relational database. So to do this, we have to come up with a bridge table between the two that will link the two tables. It will link the order with the product. And that bridge, in this case, we called it the order line or order item. Order item. Okay. The way we do this bridge table, first of all, we do it mechanically. We take the primary key of the two tables and we place them in the bridge. The primary key of the two sides of the relationship, we take the primary key, we put it in the bridge table, and those two primary keys coming from the two tables become the primary key of the bridge. So the primary key of the bridge table is a composite key. This is mechanically, we don't even need to think about it. If we have a many-to-many relationship, for us to translate it to something that can be implemented, which means to create the logical model out of the conceptual model, we create a bridge entity. And the bridge entity will have the primary key of both sides placed into the bridge, and those primary keys of both sides become composite key for this bridge table. Yep. Okay, so in this case, in the order item here, we will have. Okay, so in the order item here, we will have the order ID, which is, let's say, int. We will have the product ID, which is also int. So this is the primary key coming from this side. This is the primary key coming from the other side of the relationship. And these two become the key for this bridge entity. Plus we add if there is any extra attribute that makes sense for this bridge entity. In this case, for example, the order line, not only we say that this order includes this product, but typically we have some kind of quantity. We might order 5 items or 6 items or 100 items. So we add one extra attribute here, which is the quantity of type, let's say int, for example. Okay, and this becomes our order item. Our order item. And the relationship will be, here is one-to-many, and here is one-to-many. Sorry, I mean here the product. This is the product. Sorry. So with the product, the order item with the product will have a one-to-many relationship. And this is now fine. Database will support this. This is just to show you the importance of having a primary key for each of the entities, because those primary keys will help us to establish the relationships. To summarize, in a one-to-many relationship, I take the primary key of the one side, put it in the many side. In the many-to-many relationship, I have to put a bridge entity, take the primary key of both sides, put it in the bridge entity, and the bridge entity might have some extra attributes, I add them, and the primary key of the bridge side is the composite key of both entities that I'm trying to relate in a many-to-many. because many-to-many is not supported out of the box. That's basically the idea. Yes, please, you have a question?
So the order ID and the product ID and the order item, it will be foreign key from the...
No, sorry. The order item is the name of this entity. Sorry, it's just a bit confusing. Let me rewrite it here. So our bridge entity, what's the name of it? The order item. So what it will have as attribute, it will have the primary key of the first of the, sorry, not customer, sorry, it's confusing here. It will have the primary key of order, and it will have primary key of product. So I will have here order ID, and I will have here product ID. Product ID. These are the primary keys of the both sides of the relationship, and these two together becomes the composite key of this bridge entity. And to this bridge entity, I can add any other attribute that makes sense. In this case, for example, the quantity makes sense to add it. Yes, that's how I translate this logical, this conceptual design to a logical design that can be really implemented in a database. And I do this transformation because of the limitation of non-relational database, of a relational database. Okay, and by the way, once I do this also, automatically the relational database will enforce this referential integrity constraints as I explained before. So these relationships are very important and enforced automatically by the database. Now, if you follow kind of according to a textbook, you can have attributes that are composite when you're doing conceptual design. It's fine at the conceptual design level. But when you come to a logical design, you need to remind yourself that attributes must be atomic. They store one and one value only. For example, if I have here in my conceptual design, I might have an attribute called customer address. I should not keep it as customer address. I should break it into the pieces of the address, street, like let's say city, postcode, country, and so on. And this will give me extra capabilities when I'm doing my queries. I might say, give me all the customers in Doha, or give me all customers of Qatar, or customers of US, or something like this. If I have it all in one field, then it's much harder. Because remember, strings are not easy to manipulate. It's much nicer to just have it separate columns. Yeah? That's the whole point. So this is easy. If you find if you are doing conceptual design and you are now go into the logical design and go into the actual implementation, make sure composite attributes that are not atomic, that such as the address, you break them down into the atomic units. And for each part, you create a column or an attribute or a field. Anyway, those are interchangeable terms. The other one you might find yourself doing, or in your logical design, you might have some column. The value of that column is a multi-value. It's kind of a list. For example, employee and skills. You might have captured the skills as one column. Mm-hmm. If you discover this, you have to basically break that, because the multi-values is not allowed. In one column, you cannot have multiple values. Of course, you can trick it, so you can put comma delimited list, but that's not the point. The point is, if you want a good database design, you should not allow a column with multi-values. So if you find that column, what should you do?
New entity.
Break it into two entities. Your base entity, and the column that repeats will be a separate entity, and it will be a one-to-many relationship between your main entity and this new entity that you just discover. And then you link them. For example, here a skill, you have the employee, you kick off the skills to another entity, and you link them using a foreign key. So the primary key, because this is a one-to-many, yes? This will become a one-to-many relationship, and then basically you take the primary key of the one side and you put it on the many side to establish the foreign key relationship, or to establish the one-to-many relationship. Now, for the weak entity, we already discussed it. The weak entity, how do we establish the primary key of the weak entity? Its own partial key plus the primary key coming from the owner entity. Those two become the primary key of the weak entity. This is already discussed. Okay. Now for relationship, I already also discussed them already. So as I explained, for one-to-many relationship, you take the primary key of the one side, you take the primary key of the one side, and you put it in the many side to establish the one-to-many relationship. And that primary key, you put it on the many side, becomes what is known as the foreign key. Yeah. Now for many-to-many, I explained it already. You have to have a bridge, and in that bridge you will have primary key. Yes, primary key coming from both sides of the many-to-many relationship. Now, if you have a one-to-one relationship, so what you can do here, a one-to-one relationship, in many cases, you might have a mandatory side and an optional side. For example, you have a nurse and you have a care center, and a nurse can optionally take care or be in charge of one of the care centers. So if you have this kind of relationship, so you take the primary key on the mandatory side and you put it as a foreign key in the optional side. Okay? So it will look something like this. So the nurse ID, it becomes a foreign key in the optional side. Okay? By the way, when you take the primary key of one of the sides and put it as a foreign key, you don't need necessarily maintain the same name. You can make it more relevant or more meaningful. For example, if I could have put here just nurse ID, but it could be better to say nurse in charge or nurse ID in charge or something like this. It's more meaningful. So what I mean, it's not strictly I just take the primary key and copy it over. I can rename it if I wish. Sometimes I have a reflective relationship where, for example, in this scenario, I have an employee, and the employee can be manager of other employees. So it's a relationship involving the same entity. So the way I do it, again, I take the primary key and repeat it in the same entity. So something like this. So here is my employee table. I take the primary key and kind of repeat it as another attribute. Of course, I need to rename it because the attribute must be uniquely named. And this way, I will have employees and their managers. The manager will be just an ID. If I want the details of that manager, I will look up the details on the same table.
Yeah.
Okay, so that's
it is like self-join.
Self-join, yes. Yeah. So this is the case of self-join. But you can only do this if it is a one-to-many relationship. So one manager manages multiple employees. But in some cases, like if you have parts, and a part can be part of other components. So in some kind of factory, they have parts, and that part could be made up of other parts, and that part itself could be part of another component. So it's a many-to-many relationship, something like this, a many-to-many relationship. So in this many-to-many relationship, you cannot just take the key and like kind of have a sort of another attribute of representing the key. You have to have another entity to establish this many-to-many. So in this case, so for example here, this is the item and description and cost. And then if you want to see what are the components that make up a particular item, you need to do that in another entity. Yeah? And basically the primary key, it's like in the many-to-many. Remember the many-to-many, we have to create a bridge table. But in this case, it's a many-to-many with the same entity. So the same thing, I take the primary key of the two sides. What is the primary key of the two sides? Item ID. I put it in the bridge. Of course, I need to rename them. So in this case, I'm putting here item ID and component number and how many quantities. Okay. For example, if I have, let's say, a car as a component, it will have the car will be, let's say, item number 10. It will have wheels, for example, tire, and the quantity is 5. We will have engine, the quantity 1. We'll have, and so on. Yeah. So this way you can have the composition of an item within our inventory. So for many-to-many reflective or unary, also known as unary relationship, I will translate it in the logical design into two entities to link them in a many-to-many relationship. Okay, in terms of supertypes and subtypes, this is for the extended entity relationship. Something like this, if you remember, we have an employee as the superclass, and we have hourly employee, salaried employee, and consultant. And this is a disjoint. They could be either one of those. You cannot assume multiple roles. So in this case, we have to have a discriminator attribute. We have to have an extra attribute in the superclass to differentiate which specific type this employee is. Okay, and this usually it's a char 1, and if it's H, it's an hourly employee. If it's S, it's salaried employee. If the employee type is C, it's consultant. And the reason why this is important, this discriminator column or discriminator attribute is important.
No, which
Yes. So if I want to find out more details about the employee, for example, if I have an employee and I want to know the hourly rate, I basically, based on the discriminator value, I join to different tables. If the employee is H, the employee type is H, I will join the employee with the hourly employee to get the hourly rate. Otherwise, if the employee type is S, I will join the employee with the salaried employee to get the annual salary and the stock option. And otherwise, if the employee type is C, I will join the employee with consultant to get further details. Okay? That's how it works. Now, suppose this one is overlapping. Remember O? So, let me first show you this before I show you the O. You see here, what I'm doing here, first of all, to establish the relationship, let me first show you this. To establish the relationship between the subclasses and the superclass, of course, I have to repeat the primary key in each of those subclasses. So I can join with the superclass with the subclass. Remember the idea here, at the end of the day, I might end up, in this scenario, I might end up with 4 tables. Okay? The common data is stored in the employee. The specific data is spread across 3 tables. So when I want to get the full details of a particular employee, I need to join to one of these tables, based on the employee type. Yeah. So the actual logical design and the actual tables that I will see in my database will look something like this. So this is the superclass or the super entity, and this is the primary key of it. I take this primary key and basically add it to each of the sub-entities to be able to join. And also, it is critical in this case because it is a disjoint hierarchy or a disjoint subclass with the disjoint constraints. I must have this discriminator column. And this discriminator column will help me to decide which sub-entity I need to join with to get the complete details about an employee. Okay? Now, let's assume now, for sake of completeness, let's say this is an overlapping relationship, an overlapping inheritance, where the employee could be hourly, salaried, and consultant. Just imagine this. So how would this be translated in the logical design, in the actual database?
Maybe I don't need the employee type.
So first of all, I don't need if the inheritance is overlapping, I don't need this discriminator column. And then, how do I establish the relationships? Or how do I join?
I may have another entity that
I might have another entity. No need. What I can do. So the primary key, yes, the primary key, I will add the primary key to each of those. Yes. And the relationship will be, so this is 1 and basically 0 to 1. And here 0 to 1. And this one is 0 to 1. Yes, the relationship. So 0 to 1. And then to basically get the details, get the full details, I need to do, I need to join using this a little bit more advanced in terms of joining. I need to do left join. Okay, I need to left join these 3 with my employee to get the full details of an employee. Yeah, and I will get some duplication here.
You can do union.
I can do union. Let me see union. No, union will give you multiple records. So if I want one record that has all of these details.
We distinguish by we can distinguish by the employee type, right?
No, there is no employee type here. Because if I put employee type, it will be multi-values because they can be hourly, at the same time they could be salaried, at the same time could be consultant. Maybe let's say hourly in the weekend, full-time during the day, consultants in the holidays. You could assume all these 3 roles at the same time. Okay. In the other one, it was easy. I can just join with one of the tables and get the details. In here, I think I can do left join.
With where condition? When I put the where condition there, if there's row, it will be.
The problem is I will have, so I will join, but I will have 3 records. So my question here, I want just to get one row that has the employee details plus other details. Yes? Mm-hmm. Plus other details. Anyway, in a real world, how you will do that?
I will join with more tables in the
Maybe left join with each subtable.
No, I can do left join, of course. Left join means I will get all the employees, and basically I will get this. I think left join will do. Yes, I think left join will do it. So basically what you do, you will join the employee with every table of this. So I do employee, left join hourly employee, left join salaried employee, left join consultant. And then I will get the employee details plus if there are any other further details coming from these 3 tables. Okay.
Joined by the primary key?
Joined by primary key, of course. Remember that the primary key is available in each of these sub-entities. Yeah. So you can see here the effort we have put in this conceptual design to establish the hierarchy, or to establish the subclassing, and also to further qualify that subclass, whether it is a disjoint or overlapping. That detail is important when it comes to logical design, because if it is just disjoint, I have to put like a discriminator column, and then based on discriminator column, I will join with the appropriate table. If it is overlapping, I cannot have the discriminator column, and for me to get all the information, I will left join with all the sub-entities to get the full details in this case of the employee. Yeah. Okay. Last thing that we cannot talk about data modeling without talking about normalization. Okay. Although, as I explained to you before, in a real world, nobody does this normalization as a distinct activity. Okay. It's kind of similar to language rules. We all learn language rules and syntax and all this grammar and so on. But when we are speaking, not necessarily we are kind of applying, it becomes kind of natural. Yeah? We are using them unconsciously. We are just using them because we have been practicing the speech or practicing the language for quite some period of time. Then we don't even think about those grammar rules. Yes, that's what we do. So this is for beginners. Of course, in beginner, you are very careful. You try to apply the grammar and try not to fall into mistakes. But as you develop more skills, like it becomes natural. Same thing here. So in professional world, you don't find this stuff. But it is good to be aware of it because there are this normalization. You can think of them as some common mistakes and how to fix them. That's one way of thinking what this normalization is. Of course, this normalization behind it, a lot of math, a lot of scary stuff. But people, of course, made it more practical. So let me drive it through an example. So first, we do normalization. One of the key role of normalization is to avoid duplication. And duplication is the enemy of database designers. In fact, it's enemy of software engineers. It's enemy of everyone. Once you duplicate things, life becomes harder. But let me show you in concrete way what this means. So for example, this is a very bad design of a student table. Okay. And this breaks a couple of normalization rules. So you can see here I have student's ID, I have the advisor and the advisor room. What is wrong with this design? The advisor is repeated, and of course their associated room is repeated. What's the problem of this repetition? What is the problem that is introduced by this repetition? That is called update anomaly. So if you want to update, for example, if Smith changes his room to room 300, I have to update 2 records with that number. Okay, that's the first thing. This is called update anomaly. What's another anomaly? If I want to add student, I must know their advisor and advisor room. Suppose this is even worse if we make this not null. Cannot be null, for example. Okay. Then if I want to enter a student or insert a student, I must know their advisor and the advisor room. If they don't have these 2 pieces of information, you cannot add a student, which is a problem. Sometimes students just came in, they don't have advisor and they don't have advisor room. The advisor not even hired, they will be hired next semester. What we will say to the student? Go until the advisor comes and we find them a room. Okay, so this is an insert anomaly. You are putting more constraint unnecessarily. Okay, what about the delete? There is another anomaly which is called delete anomaly. So for example, if I delete this student, what happened is I lost some information about the instructor. I no longer have information about, in this case, John. It's gone. You see that this is the problem with data duplication. It creates update anomalies, insert anomalies, and delete anomalies. Yeah. So we try to avoid this duplication at all costs. And usually this duplication can be fixed by decomposing the entity into multiple entities. Yeah. So for example, here, what could be better design in this case, for example?
2 tables,
1 2 entities, yes. So basically here, for example, let's put first student. Let's put first the conceptual, so we are clear on this. And this is the advisor. Yep. So what's the relationship?
1 too many.
Yes, many to one. So basically, a student has one advisor. An advisor can have multiple students. Okay, just to keep it simple. Okay, so for example, here I can have student's ID. And let's say the name as an example. And in here, I will have, again, ID and name, office number, and so on. Yes? And this is a one-to-many relationship, many-to-one, if we read it this way. If I read it from here to here, it's a many-to-one. So this is the logical design. This is the conceptual design. If I make it a logical design, which is ready to deploy to the database, what should I do? No, this is the many-to-one. No need for bridge. I'll take the primary key of the one side and put it on the many side. That's how I do it. So here, because I already have here ID, I will call it advisor ID. Yeah? So and I make this advisor ID, I make it nullable. It can accept null. So I have a new student, no problem. I can insert the new student without the advisor. And when the advisor becomes available, I can assign the advisor and set the advisor ID there. If I delete the student, no problem, the advisor is still there. The advisor will not be deleted. If the advisor office number changed, I change it once in one place. See this? Basically, most of these anomalies can be fixed by further decomposition to basically avoid replication. Whenever I see replication, I avoid it. Now, there are some rules or some, let's call them some common mistakes you will find in the design. And this normalization helps you to recognize such defects or such mistakes or such problems in your design and help you to fix them. That's basically what normalization is. Okay, so there are forms. The most common kind of non-normalization rules, we call them forms. First normal form, second normal form, third normal form, fourth normal form. These are the most common ones, okay? Behind them, there's a lot of mathematical proofs and so on, but we just look at them from practical side. Okay, here is the first normal form, okay? So what the first normal form says, you can think of them as kind of rules, and you want to check that your design meets this rule. So the first normal form, first normal form is kind of a rule. Every form has associated rule. What this says, every attribute's value is atomic, which means it stores a single value. Each column or each attribute in my entity or my table stores how many values? One, and only one. Now, you can see here, in this example here, you can see this knowledge is storing multiple values, okay, comma delimited values. This is basically violating which normal form? First normal form. It's violating this first normal form. So how to fix this? That's if we just want to make the first normal form happy, we just need to, instead of doing comma in this scenario, instead of putting multiple values, I repeat the record multiple times. Of course, there will be other normal forms, they will not be happy, but the first normal form will be happy. Okay, so what I'll do here, so for example, Thomas Muller, what I will have here, I repeat it how many times? 3 times, and then with different skill. Okay, here, can you see it? That's how I do it. Same thing here, this guy has 2 skills, I repeat it twice. This one has 2 skills, I repeat it twice. This is not the best design, but according to the first normal form, is the first normal form happy? You will not get tickets from first normal form police. Halas, you are fine. Okay? So we move to the next normal form. First normal form is very easy. never have a column that stores multiple values. If you have such scenario, make sure you repeat the whole record with atomic values. Of course, this will not meet another normal form that we will see later. Okay, that's what the first normal form says. Let's have a look at the second normal form. Okay, the second normal form is only applicable when you have a composite key. Remember composite key? Made up of multiple attributes or multiple columns, okay? Now, what this normal form says, every non-key should depend on the whole key. Every non-key should have functional dependency on the whole key, not only part of the key. Okay, let's take this through an example. So employee name as an attribute, does it depend on both the employee number and product code? No, it depends only on the employee number. It has nothing to do with product code. Yes? So this design is violating the second normal form. Let's look at the other one, project name. Does the project name depend on both employee number and project's code?
No.
No, it depends only on the project code. Yes? Now, the last one, the total days on project. The total days a particular employee spends on a project. Does it depend on only the whole key, or only part of the key? The whole key. So the total number spent on project depends on two things. Depends on which project are we talking about and which employee are we talking about. So which ones are violating this rule of dependency on the whole key? These two columns. Once I find that the presence of some non-keys not depending on the whole key, then I have this anomaly of violating the second normal form. And how I will fix this? Breaking down things. So let's try to fix this. What do you think? So the ones that are, so this one partially depends on this. So I will put them together. Yes? So I'll put here, first I will have here employee entity. And what it will have? The number and the name. So these are dependent, so I put them separate. And the other one, the project. Yes, the code and the name. And then basically I will have my, okay. No, all right, no problem. Yes, so I will have here my project employee. And in here, as you can already guess, this is the primary key of this one. This is the primary key of this one. And basically what I'm doing here, I am bridging these two. Okay? So the project code with the employee number will become basically the composite key of this table, of this entity. And then I'll take this one that depends on both and put it here. This is the days. Days will be. Okay? And then basically this is a one-to-many relationship and this is a one-to-many relationship. Okay? So that's how I fix this. And this now, every non-key depends only, first of all, in here remember, second normal form, we only apply it if we have a composite key. So this is already not applicable. Second normal form, not applicable. Second normal form, not applicable. It's only applicable to this entity. We ask ourselves, this one is a key, is a composite. Now this is the only non-key, days. Do days depends on the whole key or just part of the key? The whole key. Khalas, that's it. This design satisfies the second normal form. Clear? Okay, moving on, the third normal form. The third normal form, what the third normal form says, that the keys, sorry, the non-keys should have dependency only on the key, only on the key. They should not have dependency on a non-key. Attributes of my entity should only have a functional dependency only on the key. They should not have a functional dependency on a column that is not a key. Yes, that's what this says. That's what this third normal form says. So which means all fields are functionally dependent only on the primary key. Okay, so let's have a look what this means. Okay, so here the name is functionally dependent on the customer ID. Okay, the salesperson, so which means like it makes sense so if I have the customer ID, it makes sense to associate it with the name, associated with the salesperson serving this customer, and the customer ID will have a region. They might be in a north region or south region or Asia Pacific region and so on. But also we have this dependency here between the salesperson and the region. Because basically the salesperson manages certain region. So the region not only depends on the primary key, depends also on another non-key. Yeah? In third normal form does not like this situation. It does not like you to have fields or attributes depending on something other than the primary key. Okay, so what we do here, anything not depending on the primary key, we kick it out to a separate entity. So we will have a separate entity for salesperson, and it will take the region with it. And so I'll have salesperson, and I will have a customer, and then I link the two. That's how I do this. So I will break it down. So something like this. So something like this. So instead of having salesperson, so instead of having the salesperson and the region, I take the salesperson and the region in a separate entity, and then basically link them. Okay. So this basically link the two. Yeah. That's how I do it. Okay, because I really need to move on. Fourth normal form. What fourth normal form says? No repeating group. No repeating group. Which means this scenario that we fixed before, if you remember the first one, this one is not meeting the fourth normal form. In here I have a repeating group. So I have here a repeating. This student here is repeated 3 times. This one is repeated 2 times. This one is repeated 2 times. These are repeating groups. This is not allowed according to the fourth normal form. Okay, so how do I fix this? Again, through decomposition. So in this case, what I will do, so first I will split this into 2 entities. So for example, I could have, let's say, student, yeah, and then I have here, yes, first name, last name. I could have an ID and so on. And in here, I will have, yes, the knowledge. Knowledge, whatever. It's very poor names anyway. We just need to fix this as it is. Okay? And then basically, the relationship here will be one-to-many. Yeah? Yeah, that's fine. One-to-many. This is student knowledge. Again, this is a poor design. It's still not perfect, but not too bad. This is let's say this is an ID here. We might have an ID here. So this is my primary key here. So because of one-to-many relationship, I repeat here I bring the primary key and put it in here. This is the student ID. This is the student ID. Okay, so in this case, the students will only be mentioned or inserted once in the student table, and then I will have multiple entries for the knowledge in the knowledge table, and both of them are linked using the student's ID as the primary key. Yes, so that's basically how I avoid the repeating groups. So this normalization is still relevant. You still need to be aware of it, but try to apply it while you're doing your design. Basically, keep in mind those basic principles or basic rules that every column should have single value, atomic values, not multi-values. That's first normal form. Second normal form, if you have a composite key, all the attributes should depend on the whole key, not only part of the key. Yeah? If you have such scenario, you need to do decomposition. The third normal form, all known keys should depend only on the key. It should not depend on something other than the key. Anything depending other than the key, kick them out into separate entity. And the last one is no repeating groups, no repetition in your data entries. If you have repetition, split again to avoid that repetition.
Is there repetition in multiple columns?
Repetition in, yes, basically multiple rows have duplicated data. That's what this means. Yeah. So for example, the first name, last name is repeated.
Yeah,
Because, yes.
The ID will be repeated, the knowledge.
ID is fine.
Yeah.
Primary keys to be repeated, it is fine. It is a must. Otherwise, we cannot establish the link. Primary keys, yes, this is a valid point. Primary keys are duplicated, it's fine. Because that's the only way we can link the two. But by the way, primary keys are very, very stable. First of all, almost they don't change. Our student number, even if I noticed some students went away for very long and they are welcomed back, and guess what? Their ID is the same. It does not change. It's very, very stable. It's fine to repeat. But address, phone number, title of the course, skill, keep changing all the time. Okay, so we don't want to repeat those at all. We don't want to repeat them because they are so volatile. We don't want to repeat them. For primary keys and those things it's basically the mechanism to establish the link without duplicating the primary key in the mini-site table. We cannot establish the link. Yes? Okay. That's it for data modeling.